So electrodynamics, charge in motion. So firstly we have to start from the motion of the charge, current. Okay, so what is the current? Rate of flow of the charge, or number of charges passing through a specific point per unit time, is defined as a current. So please be silent. That will be defined as a current. Rate of the change, yeah, rate of the charge passing through any point per unit time is defined as a current. Yeah, mean current is I. We know that infinitesimal change is measured in the form of derivative with respect to time. R equal to R naught means the specific point, any particular point. Okay, mean if this is a line, so the charge passing through from this point, that will be defined as a current. Okay, एक point आप choose कर लेंगे और उसमें जितना charge गुजर रहा है उसके per unit time, that will be defined as a current. Okay, what is the unit of current? Ampere. Yes, current, unit of the current is ampere, and that will be equal to actually current is charge per unit time, so the unit of charge is coulomb and unit of time is per second. Okay, so per second, or you say that second per month. So this is the unit. Okay, current is vector quantity or a scalar quantity, because actually direction counts, but they all direction is important in current. If the charge is the direction of the flow of the charge is will represent the current, but it doesn't affect in the summation or resultant. Mean if some current is from due to positive charge, and that will be from A to B, and other is B to due to negative, and that is from B to A, then 2 ampere plus minus 2, I mean that must be a 2 ampere minus 2 ampere, but that must be a 0, but that will be equal to 4. So that don't hold the law of vector addition. That's why that is not a vector, क्योंकि उसकी डायरेक्शन जो है वो काउंट नहीं करेगी. So current is not a vector quantity, but and it is not necessarily the current is always passing through the wire. It may be a wire may be a thick cylinder, wire may be a thick wire, and thick wire will be always behave like a cylinder. So there will be there may be the surface of the cylinder. Okay, so current may be passing through the from the surface of any cylinder. So that's why we have to define the current density, as we have defined the density in the previous lectures about current density, surface density, current charge per charge density. Okay, surface charge density, volume charge density, and linear charge density. But in the case of current density, we will consider only the surface density. So current is there is current density that is current per unit surface. Surface is area, as I have already explained in many and many times. Surface is area. Okay. So current density is representing by the J. Okay, and that will be equal to di over ds. Okay. Yes. When we multiply a scalar with a vector, the resultant will be a vector. We will see that the current density will be a vector quantity. Why that will be vector, we will explain it little bit later. So this is current density. The current density is representing by the J. Change in current per unit surface will be defined as a current density. And what will be the unit? The unit of current density, that will be equal to the unit of current is ampere, yes, and the unit of surface is area and multiple of the two length, and the area of the length is meter. So ampere per meter square, or you may say that ampere meter. Okay, so this is the unit of the current density. Okay, and di is actually the J dot ds. There will be a dot product between because surface is a vector and current density will be also a vector quantity. Also, that's their dot product will give the this. Okay. Result is scalar. When we take the actually product is nothing. I have already explained. Cross product is area, and for area is a vector quantity. That's why. And the dot product is actually not multiplication. It is effect of one vector on another. We have our so current density passing through the surface is then defined as a current. So that's why we are taking the dot product. And so current I will be equal to as we know that there is change according to the surface. So the integral will be a surface integral. So the result will be a J, and this integral will be a surface integral, not linear integral, but it is a surface integral. I have already explained the linear integral mean the integral along the line. The surface integral mean the integral along the surface, and that will be a double integral. That will be a 2. So that will be J dot d alpha cross alpha beta are a two length. They may be a okay, two length of the parallelogram. Okay. And why parallelogram surface is not necessarily that is the parallelogram. Why we take a parallelogram? Because we are integrating and we are considering the infinitesimal small. So every curve path will behave like a parallelogram. Okay, so that's why this will be a. Please be silent. If you have any question, raise your hand, and I will definitely try to answer that. Okay. So this will be your current density. Oh, sorry, this will be your current. Okay, current in the form of current density. Okay. Next topic is about the Ampere law. Like same as Gauss's law for the charge, the Ampere law is associated with the current and magnetic field. Okay. So जी क्या इसको because the area surface is multiplication of two lengths. 1 minute. J is di over ds. Since we are since surface is always a multiplication of two lengths, that's why that will be a two integral. For one length, we will consider one integral. For two in area is always a multiplication of a two lengths. One length is defined as alpha, and one length is a beta. Why I am considering the cross product of parallelogram? Because I have already explained the shape of the surface may be any shape, but when we divide it into these small patches, and so small that is infinitesimal small, then one patches will be treated as a parallelogram. Okay, all patches will be, if that is a infinitesimal small, d alpha. Actually, this is not a parallelogram. Even small patches are not, but when we divide it into this so small that become a infinitesimal small, and this length become a d alpha, and this length become a d beta. Derivative mean approach to zero, so small that then every line will be treated as a straight line. So that length become a, that curved line will become a straight line, or that become a parallelogram. So this small surface will be a the alpha cross beta. When we integrate it, when we sum these path, it means we have to consider the integration. So that's I have already explained in the topic of the uh, uh, and charge distribution and flux. In the topic of flux, we have explained all these. Okay, so this okay. Next topic is about the Ampere law. What is the Ampere law? Okay. Ampere law. It is also defined Ampere circulating law. Okay. Ampere law. What is the Ampere law for electromagnetic? Ampere law is total magnetic field along the closed line, not open line. The Ampere law is actual law is not Ampere law. Actual law is the Berer-Servet law that explain the magnetic field very thoroughly and briefly, but that is difficult. That's why that is excluded from your course, because lot of integration involved in the Berer-Servet, but that is actual law. Okay, but Ampere law is as compared to simple, but it is not complete, because you have to consider what is Berer-Servet law itself tells what will be the shape of magnetic field and what is the result. But Ampere law will not, we have to already familiar with what type of magnetic field will be produced, and we have to consider that magnetic field along the path. That's why. But that is simple, and your course is related to the computer science, and so that's why we are trying to avoiding the heavy integrations. Okay, so that's why we will take start from the Ampere's law. We are not discussing the Berer-Servet. Okay, so if you was if you are not a BS computer science student, and if you are a physics student, then we must discuss that. That law was more important than Ampere. What is the Ampere law? Total magnetic field along closed line will always equal to mu naught times total current enclosed. Okay. So total magnetic field, yes, total magnetic field. Magnetic field is uh, total is representing for discrete. Total is representing when you are summing something, then that will represent. If that is discrete, we will sum. If that is continuous, we will integrate. Okay. So total will replace sum. Magnetic field will be replaced with the B. Along will be replaced with the dot, and line equal mu naught times mean multiplication. Okay. So for discrete total sum A equal to 1 to magnetic B along dot close line delta L. Sum will be, because magnetic field is external magnetic field is constant. So if there is a summation, they will be they are different paths, L1, L2, L3. Equal to line always equal to mu naught times current, total current enclosed. So if here is A, here must be a B, because this summation is on the line, and this summation on a current. Okay, so you may write. If this is A to N, this will be B to N. Why we are considering the M only to differentiate? That is a different thing. Mean that this summation is different, this summation is different. This is A to N, and this is B to M. Okay. The left side is also a scalar quantity, right hand side is also a scalar quantity. Okay. So this is a for this three. This is a for this three. For continuous, yes. For continuous, this summation will be replaced with the integration. So and this will be, because this is a line, this will be a single entity. Okay. Because line is a single entity. B dot and and this is a total magnetic field along the closed line. Continuous line is representing by the single integral. Continuous surface is is representing by the double integral. Continuous volume is representing by the triple. Since this is a single integral, so we because it is along the line, so we have to consider the single integral. The other thing is that is the close. Close means you have to come back to the initial point again. So if the line is closed, there will be a no boundary value, because it will be from A to A. I mean, it will be so we have to consider this sign, means this close counter or a circle represent actually this line integral is a close. It is not from A to B, but it is from A to A. I mean, you have to come back to the. Okay, so that will be representing the closed line integral. Okay, that will be equal to mu naught this sign represent the closed line. Closed line means when you come back to the initial point again. Mean if you move from A to B and B to C, C to D, D to A, and then come back to DA. Mean in every case you will come back to the initial point. So this line, this closed circle means the closed lines, nothing else. Okay. When we take the examples, it will be I will clarify on in different examples. Okay, like examples of the toroids, solenoid, wire, etc. Okay. But what is the I? I is there are two. This is a integral form of the Ampere law. Okay, there are two form of the Ampere law. One is defined as the integral form of the Ampere law. One is defined as a differential form of the Ampere law. As in the case, as we have done in the case of Gauss's theorem, the differential form of Gauss's theorem was not part of your course. Similarly, differential form of the which is difficult, that is not part of your course. That is excluded from the course. Only Ampere law, the simplest form of Ampere law is included. Okay, so that's the Ampere. Okay, so this DL is not different. This DL, which will be along this current, and this current is not total current. Always remember, this I is always, it is very important to note. This is also enclosed. This is also, this is current enclosed, not total current. Be careful about that. Like a Gauss's theorem. Okay, exactly the same as Gauss's theorem. So this is not actually the simple I. This is enclosed I. Okay. Okay. Yes.
Circle if with the DI because both the summation are same as like what we are at the time. Summation table one और expression table B से can have to follow close ना
No, no, that is different. This close and trigonal, both are close, but this this current is not close, but this is current closed by this line. This line. When we discuss the example, that will be a okay.